Hello there! In this series of videos I'm going to be talking to you all about forces for your CIE GCSE physics course. So in this first session we are going to look at the classic equation, Newton's equation, force is equal to mass times acceleration. This is really the underpinning of pretty much all classical physics. So classical physics is a physics about stuff moving, me throwing stuff, stuff hitting something else. F is ma, and these laws that we're going to learn in the next unit, they are the bedrock of our modern physics. So really, really important stuff. So we're going to start off with a quick recap, and you should remember from the last unit that we did on motion that we have this term of acceleration. So acceleration is the rate of change of velocity. So whenever you see a term like this that says a rate of change, a rate of something always means per second. Or, if you want to be really pedantic, we could say per unit time. So it means how much is the velocity changing per time. So to find that, we need to do the change in something's velocity divided by the time that took. Now, in most of physics, we use a couple of special letters. We always use the letter U to be the initial or starting velocity of an object. We use V to be the final velocity of the object. We use T for time and A for acceleration. Worth noting, we also use S as displacement, or distance from where I started. I started saying distance, now I can't spell it. Displacement. But we're not going to use that one in this equation. So this equation can equally be written as the change in velocity. So to get the change, I want my final velocity take away my starting velocity. That gives me the velocity difference, divided by t. And I say that's in units of meters per second squared. So why is it meters per second squared? Well, my change in velocity, that is measured in meters per second, and I'm dividing it by something in seconds. So I get meters per second, and I'm dividing it by seconds. And if you think about what that means meters divided by seconds divided by seconds. So that's just the same as saying meters divided by seconds squared, or meters per second squared. That's a bit more A-level-y, but it's worth remembering. Okay, so this is the classic experiment that you're going to do. You're going to have your bench across the classroom, and you're going to put a truck or a trolley on it. And then with some string, you're going to have a mass. Now the idea is the mass is going to hang off the edge of the bench, and it's going to have a force acting downwards on the trolley. And what that will do is give me an equal force along the string. So what I get is an acceleration force acting on this trolley. And what you'll do in the lesson is measure the acceleration of the trolley. But what I want you to do is just think about what will happen if I have a very, very light trolley, and what will happen if I have a very heavy trolley. So in other words, how does the force that you push something affect its acceleration, and how does the mass that you push something with affect its acceleration? Well, let's go back to this slide. I'm going to give force the symbol, just to remember for later, of F, and I'm going to measure it in newtons. The newton is the classic unit of force. All forces are measured in newtons under the SI system. Acceleration, I'm always going to give the symbol A, and that, as I've said before, will have units of meters per second squared. And I want to know how the mass of my object, which I'm going to call m, measured in kilograms, affects it. So let's just think about this idea. Let's say I start with this mass. I have my trolley, and I record its acceleration. So let's just say, for instance, acceleration is 5 meters per second squared. Let's say I add on some extra masses here so that my force gets even bigger. I have a big force now, big force here. So what will happen to my magnitude of acceleration? You can probably work out that my acceleration is going to go up. So I can say, just as a little note, if force increases, acceleration increases. And I'm using that kind of notation, and you might want to do this yourself in an exam. Just jot down little ideas at the side of the page. Now let's think, well, what will happen if I make this trolley really, really, really heavy? So if I start stacking extra masses on top of it. The trolley is really heavy and I've got the same force. What will happen to the acceleration now? Well, again, you should probably be able to think, if you imagine trying to push a car, cars are heavy, and they accelerate very, very slowly. You need a big force to make it accelerate. So I can also say that if the mass increases, acceleration goes down. So, remember, I'm trying to do something that has force, mass, and acceleration. And I know that if force goes up, acceleration also goes up, but I know that if mass goes up, acceleration goes down. Now, depending on how good you are at maths, you might have learned a bit of proportionality. Don't worry if you haven't. If this next bit goes over your head, don't worry, I'll tell you when to tune back in. I can write this first equation, that if force goes up, acceleration goes up, as saying force, or sorry, no, I'm going to say acceleration is proportional to force. They're directly proportional. For this one, if mass goes up, acceleration goes up, I can say that acceleration is proportional to 1 divided by mass. In other words, they are inversely proportional. I'll write that down there. Inversely proportional. That funny little fish symbol is called an alpha, and this just means that they're proportional. So what does that mean? Well, there's a cool little trick in maths. Ask your maths teacher to explain it to you if you're interested, because it is quite cool. That means that I can say, therefore, that acceleration is equal to force divided by mass. And usually I'd do some extra manipulation, but in physics we've said we're just going to let that become, our equation, and we're going to say acceleration is equal to force divided by mass, and if I rearrange that, I get force is equal to mass times acceleration. F is equal to ma. This is a really important, really classic bit of physics that you just need to know. So let's do a quick checkpoint and see how well we've understood that. So I want you to imagine that I have a train with a total mass of 7.5 times 10 to the 5 kilograms. That's quite neat. There's no conversions or anything that we need to do there, so I'm quite happy with that. And it says the train accelerates, so I might remember that's got the symbol A, from rest. Now from rest, this means that my initial velocity u is 0. At a constant rate, that might be important, along a straight horizontal track. It reaches a speed of 24 meters per second, so there I can say v is 24, and it takes 60 seconds, which is t. T is 60. So I'm first asked for acceleration. So I need to remember the equation. Acceleration is v minus u over t. My v, so that is equal to 24 divided by 60. And I'm just going to plug that into a calculator because I can't do that in my head. 24 divided by 60 is 0.4. And I must always include units. So that's meters per second squared. And it's always worth just writing it on the line as well, where the examiner expects it. And then ask for the resultant force acting on the train. Now over here, I was given the mass of the train, m. So now I have A. So now I can use force is equal to mass times acceleration. So my force is equal to my mass, which was up here. So that's 7.5 times 10 to the 5. And I'm going to multiply that by my acceleration, which is 0.4. And again, just grab my calculator. So that comes to 300,000 newtons. Or if I want to be fancy, I could say 300 kilonewtons, but I don't have to. I could just leave it as 300,000, or I could leave it as 3 times 10 to the 1, 2, 3, 4, 5 newtons. Either one's fine. That's it for forces. I'll see you back next lesson when we are going to talk about Hooke's law.